In this series of videos, I will discuss some of the subjects that students often struggle with in math. In this particular video, I will discuss some operations with decimals. If you have not already watched the video on fractions, I encourage you to watch that video before you watch this one, as you will need to understand some of the concepts in that video before you will be able to understand some of the explanations in this one. This slide shows the topics that I will discuss in this video as well as the numbers of the slides so that you can fast forward to the topics that interest you. The slide numbers are located in the lower right hand corners of the slides. This chart shows the names we give to some of the place values in our decimal system. Note that, other than the ones place, each place after the decimal has a corresponding place before the decimal, but they go in reverse order. Also note that we put a THS on the ends of the names of the places after the decimal. To read a decimal number, you should read the whole number like you normally would. Then, to say that a decimal point comes next, say the word AND. To read the numbers after the decimal, we say the number like we normally would, and then we say the place value of the last digit. For example, we read the number you see on the last line of the screen by saying 203 and 51 thousandths. Note that I did not say 203 and 51 thousandths. This is because the word AND tells you that a decimal goes there. And of course there is no decimal between the 2 and the 3. Now, let's talk about equivalent decimals. You do not change the value of a number when you add zeros on the end of a number as long as you put them after the decimal point and after the last number. Also, if a decimal point is not stated, you should assume that it goes after the last number. These rules tell us that all three of the numbers you see here have the same value, and you should realize that this is true because 16 is equal to 16 and 0 tenths, and both of these are equal to 16 and 0 ten thousandths. You should also realize that 3 and 7 tenths is equal to 3 and 70 hundredths, and both of these are equal to 3 and 7,000 ten thousandths. However, you should also realize that 5 and 3 tenths is not equal to 5 and 3 hundredths. Note that the 0 was inserted between the 5 and the 3 and not after the last number here. Now, let's talk about adding and subtracting decimals. To add or subtract decimals, you must start by lining up the decimal points. You can then add or subtract as indicated, bringing the decimal point straight down. For example, to add 14 plus 3 and 47 hundredths plus 12 and 3 tenths, you must begin by lining up the decimal points like you see here. Note that, as I said in slide 4, I can add the decimal point and 2 zeros on the end of the 14 without changing the value of the number. Also note that, as I said in slide 5, I can add a 0 on the end of the 12 and 3 tenths without changing its value. Now we can add like we normally would, bringing the decimal point straight down. To see why this rule works, note that we can write the decimals as mixed numbers, and so this problem is equivalent to the one you see here. To add these mixed numbers, I will use the method I called method number 2 for adding mixed numbers in the video on fractions. I must get a common denominator, and then I can add the fractions and whole numbers separately. Now, let's work an example that illustrates how we can subtract two decimals. Again, we must start by lining up the decimal points. Note that I can add a decimal point and 2 zeros on the end of the 150 without changing the value of the number, and so I can set this problem up as shown here. Now I can subtract like I normally would and bring the decimal point straight down. To see why this rule works for this example, you need to realize that I can rewrite 8 and 21 hundredths as a mixed number, and so this problem is equivalent to the one you see here. Now, I can subtract 150 minus 8 and 21 hundredths using the method I called method number 2 for subtracting mixed numbers in the video on fractions. Now let's look at how we multiply two decimals. To multiply two decimals, you can begin by multiplying the numbers as if the numbers are whole numbers. Then place the decimal in the answer so that the number of digits behind the decimal in the answer is equal to the total number of digits behind the decimals in the problem. So, to multiply 31 hundredths by 2 and 9 tenths, we must begin by noting that 31 times 29 is equal to 899. Then, we can note that there are a total of 3 digits behind the decimal points in the problem, and so we must place the decimal in the answer so that there are a total of 3 digits behind the decimal point. This tells us that we get 899 thousandths when we multiply 31 hundredths by 2 and 9 tenths. To see why this rule works for this example, you need to realize that I can rewrite this problem as the problem you see here. You should be able to see that you get 899 thousandths when you multiply 31 hundredths by 2 and 9 tenths. Next, let's talk about how we divide two decimals. If the divisor, or the number on the outside of the division symbol, has a decimal stated, you must begin by moving this decimal to the end of this number. When you do this, you must move the decimal in the dividend, or the number on the inside of the division symbol, the same number of places. You can then divide as you normally would, bringing the decimal in the dividend straight up. To divide 8 1/10 by 3, we can begin by setting the problem up like this. There is not a decimal point in the divisor stated, and so we can assume that it is already at the end. This means that we can divide as shown here. Since we bring the decimal in the dividend straight up, I must be careful about where I place the numbers in the answer. Note that I put the 2 above the 8 and not the 1 because I can divide 8 by 3. To see why this rule works, note that I can rewrite this problem as shown here. And if you think about the rules we use to divide fractions, you should be able to see that 8 1/10 divided by 3 is equal to 2 7/10, which, of course, agrees with the answer I got earlier. Now let's look at another example. To divide 15 9/10 by 53 hundredths, I can begin by setting the problem up like this. Now, because the divisor has a decimal stated, we must begin by moving this decimal 2 places to the right. When I do this, I must also move the decimal in the dividend 2 places to the right. Note that I can add a 0 after the 9 in order to do this. Now I can divide 1,590 by 53. Again, since I want to bring the decimal in the dividend straight up, I must be careful about where I put the numbers in the answer. I put the 3 above the 9 because the 9 was the last digit of the dividend I used in the first division step. In other words, I could divide 159 by 3, but I could not divide 1 or 15 by 53. To see why this rule works for this example, you need to realize that this problem is equivalent to the division problem you see here. To divide 15 9/10 by 53 hundredths, you must begin by changing the 15 9/10 to an improper fraction, and then you can copy down the first fraction, change the division sign to multiplication, and flip the second fraction. I'm going to use the second method to multiply fractions that I discussed in the video on fractions. Before I multiply straight across, I will divide both the 100 and the 10 by 10. I could also divide both the 159 and the 53 by 53, but I'm going to choose to not do this so that you can see why this rule works. As I will discuss in further detail momentarily, you can also look at the fraction bar as a division sign, and you should be able to see that this problem is equivalent to the decimal problem I just worked. Of course, when we finish simplifying this, we find that the final answer to this problem is 30. Let's look at one more example that shows how we can divide decimals. In this case, I must move the decimal in the divisor 3 places to the right in order to make the divisor a whole number. And, of course, when I do this, I must move the decimal in the dividend 3 places to the right also. Note that I must put a decimal after the 7, and then add 3 zeros after the decimal in order to do this. Now I can divide 7,000 by 8. Note that I put the 8 above the first 0 because the first 0 was the last digit I needed to start the division. To see why this rule works for this example, note that this problem is equivalent to the one you see here. Now let's talk about how we can convert between fractions, decimals, and percents. As I mentioned earlier, a fraction bar is really a division sign. So, to convert a fraction to an equivalent decimal, you can divide the numerator by the denominator. For example, To convert 9/20ths to an equivalent decimal, you can divide 9 by 20, as shown here. This tells us that 9/20ths is equal to 45/100ths. We have several methods that we can use to convert 3 4/5ths to an equivalent decimal. If you want to use the first method I've shown here, you can begin by finding 4 divided by 5, and then, since we want to find an equivalent decimal for 3 4/5ths, and since the word "and" means add 3 to this answer. You could also start by converting the 3 4/5ths to an improper fraction, and then converting this to a decimal. Note that 3 4/5ths is equivalent to 19/5ths, and that 19 divided by 5 is equal to 3 8/10ths, as shown here. Note that both of these methods tell us that 3 4/5ths is equal to 3 8/10ths. In this slide, I'll talk about a concept called repeating decimals. To change 4/9 to an equivalent decimal, we must begin by dividing 4 by 9. To do this, we can put a decimal after the 4 and then add 4 zeros, as shown here. You should be able to see that there is a pattern that repeats when we do the division, and you should also be able to see that this pattern will continue forever if I continue to add zeros. To show that the pattern continues on forever, I put a horizontal segment over the digit or digits that repeat, which in this case is 4. It is important to note that I could also write this decimal using one of the notations you see in gray here, because they all show that the 4's continue on forever. In fact, there's an infinite number of correct answers to this problem, but it would not be correct to say that 4/9 is equal to 0.4, 0.44, or anything of the sort without the horizontal segment, because 4/9 is not exactly equal to 0.4, 0.44, or anything of the sort. To convert 8/11ths to an equivalent decimal, we can start by dividing 8 by 11, as shown here. You should note that if I add more zeros onto the end of the dividend, the pattern you see here will continue forever. So, to write 8/11ths as a decimal, I can write 0.72 and then put a horizontal segment over both the 7 and the 2 to say that the pattern continues forever. Or I could also use one of the notations you see here. To find an equivalent decimal for 2/15ths, I must, of course, start by dividing 2 by 15, as shown here. Notice that this example is different from the other two because only the 3 repeats. To show this, I put the horizontal segment over only the 3 in the answer. Or, if you prefer, you could use one of the notations you see here instead. Note that all of these notations show that only the 3 repeats. Next, let's talk about how we can convert decimals into equivalent fractions or mixed numbers. To convert a terminating decimal, or, in other words, a decimal that stops and does not repeat, into an equivalent fraction or mixed number, you can just read the number and write what you say in the form of a fraction or mixed number. For example, we can say that 0.32 is equal to 32/100ths, which reduces to 8/25ths. We can also say that 152.9 is equal to 152 9/10ths, and we can say that 3.016 is equal to 3 16,000ths, or 3 2/125. As I said earlier, these are all examples of terminating decimals. This means that they stop and do not repeat. To convert a repeating decimal to a fraction or mixed number, you need to do some algebra, and we'll discuss that in the next 3 slides. To convert this decimal to an equivalent fraction, we will begin by writing an algebraic equation. We will say that x is equal to this decimal using the horizontal segment notation. Next, we will multiply both sides of the equation by 10. I'll talk more about why I chose 10 when I work the next example. Note that 10 times x is equal to 10x, and that, when we multiply the decimal by 10, this will move the decimal one place to the right. Next, we will subtract these two equations from each other. Note that 10x minus x is equal to 9x, and that 3.3 repeating minus 0.3 repeating is equal to 3. Now we can divide both sides of this equation by 9. Note that 9x divided by 9 is equal to x, and that 3 divided by 9 is equal to 3/9, or 1/3. Since x represented the decimal 0.3 repeating, this tells us that 0.3 repeating must equal 1/3. Now let's talk about how we can convert this decimal to an equivalent mixed number. Again, I'll start by saying that x is equal to this decimal using the horizontal segment notation. Next, I'll multiply both sides of this equation by 1,000. In this example, I'm choosing to multiply both sides by 1,000, which, of course, is a 1 followed by 3 zeros, because there are 3 digits that repeat. You might recall that I multiplied both sides of the equation in the last slide by 10, when there was only 1 digit that repeated. Next, I'll subtract these two equations from each other. 1000x minus x is equal to 999x, and 4158.158 with the 158 repeated minus 4.158 with the 158 repeated is equal to 4154. Now I can divide both sides of this equation by 999. 999x divided by 999 is equal to x, and 4154 divided by 999 simplifies to 4 and 158 over 999. Since x represented the decimal I wanted to convert to a mixed number, this means that the final answer to this question is 4 and 158 over 999. For my next example, I will convert 7.081 with the 81 repeated to an equivalent mixed number. Like I did in the last two slides, I will start by saying that x is equal to this decimal using the horizontal segment notation. Now, since there is one digit after the decimal that is not repeated, I will multiply both sides of this equation by a 1 followed by 1 0, or, in other words, 10. And you should be able to see that this will move the decimal in the number to the right one place. Next, since there are two digits that are repeated, I will multiply both sides of this equation by 100. You should be able to see that this will move the decimal in the number to the right 2 places, and that 10x times 100 is equal to 1000x. Now, I can subtract these last two equations. 1000x minus 10x is equal to 990x, and 7081.81 with the 81 repeated minus 70.81 with the 81 repeated is equal to 7011. Finally, I will divide both sides of this equation by 990 and simplify my answer. I have now shown you how you can change repeating decimals and decimals that stop into equivalent fractions and mixed numbers. If a decimal does not stop and does not repeat, it is called an irrational number, and there is no equivalent fraction or mixed number. This means that there is no way to turn the decimals you see here into equivalent fractions or mixed numbers because the 3 dots on the end say that the pattern or lack of pattern continues. I know that you can see a pattern in the second number you see here, but you should notice that I cannot use the horizontal segment notation to write this decimal, and so it is not actually what we would call a repeating decimal. Also, I know that a lot of people believe that pi is equal to 3.14 or 22/7, but this is not true because these numbers are only approximations for pi. Pi is actually closer to 3.14159.265, and even this is only an approximation. Now, let's talk about converting fractions and decimals to percents and vice versa. To convert a percent to a decimal, you can move the decimal point 2 places to the left. So, for instance, I can say that 3% is equivalent to 0.03, and I can say that 215% is equivalent to 2.15. To see why this rule works, recall that percent means per hundred. This means that 3% is equal to 3 hundredths, which, of course, is equal to 0.03, and 215% is equal to 215 hundredths, which, of course, is equal to 2.15. To convert a decimal to a percent, you can move the decimal point 2 places to the right. For example, 0.7 is equivalent to 70%, and 0.041 is equivalent to 4.1%. To see why this rule works, recall that percent means per hundred, and note that 7/10 is equivalent to 70 hundredths, or 70%, and that 0.041 is equivalent to 41 over 1,000, and that, if we divide both the top and bottom of this fraction by 10, we find that it is also equal to 4.1 over 100. To convert a fraction to a percent, you can begin by writing an equivalent fraction with a denominator of 100. Your answer to the question will be the numerator of this fraction. For example, to convert 8/25 to a percent, you could start by multiplying both the top and bottom of the fraction by 4. This tells us that 8/25 is equal to 32 hundredths, and so 8/25 must be equivalent to 32%. Or, if you prefer, you could convert this fraction to a decimal, and then convert the decimal to a percent. For this example, you could note that 8 divided by 25 is equal to 0.32, and so 8/25 must be equivalent to 32%. As another example, to convert 1/8 to an equivalent percent, you could start by noting that 8 times 12.5 is equal to 100. And so you would need to multiply both the top and bottom of this fraction by 12.5 to get an equivalent fraction with a denominator of 100. Then, of course, you could say that 1/8 is equivalent to 12.5%. You could also work this problem by converting the fraction to a decimal, and then convert the decimal to a percent. This means that you could start by noting that 1 divided by 8 is equal to 0.125, which is equivalent to 12.5%. To convert a percent to a fraction, you can write a fraction with the percent as the top number and 100 as the bottom number. For example, we can say that 93% is equivalent to 93 hundredths. This cannot be simplified any further, and so it is our final answer to this question. Or, if you prefer, you can convert the percent to a decimal and then convert the decimal to a fraction. For this example, you could note that 93% is equal to 0.93, which, of course, is equivalent to 93 hundredths. As another example, we can say that 115% is equivalent to 115 hundredths, which simplifies to 1 3/20. Or, if you prefer, you can convert the percent to a decimal and then convert the decimal to a mixed number. To work this example using this method, you would begin by noting that 115% is equivalent to 1.15, which is equivalent to 1 3/20. If you have comments or questions about this video, please feel free to contact us using the Contact Us link on our website.